thing that we need to do is make sure that this math works out. There's one little trick to do. That at the first hour you were used to this. Something that will make it work that I forgot to mention because I don't know, I was in a hurry. So let's talk through this together. I hear a deep bass voice. Not sure who it is. Oh, it's Jagrin. Actually, I did know who it was. All right. We use this equation to do these math problems with these wavelengths. Is that about right? Now, I found this one on the internet, so it's more specific. We probably didn't have these exact numbers, but we were close. Is that right? Don't worry about the 397. That's just the end. So 410, 434, 486, and 656. Were we close? Okay, well, let's just do this one right here. 656. What did we call it? 655. Wow. I'll take that. So when was everyone okay finding the energy from this point? E equals hc over lambda, correct? All right. So we just need to plug in h and c and then divide it by 656. If you've put it in your calculator, this is a 10-second process. So what does the E equal here? Someone already have that? What's that? 3.03 times 10 to the negative 19. All right. Yeah, that's fine. If there's still 6 more of these calculators if you need to borrow one. All right. So we had that value. 1, 2, 3 left. Good job. All right. The thing that we need to realize is this is energy given off as light, right? So it's energy given off. If it's energy given off, this was the part in first hour that I forgot to say, then this answer, when we plug it in here, needs to be a negative value. It's energy radiated or lost from the atom, so it's an exothermic process. So it has a negative sign. All right? So now I'm going to plug this in, and the math will work out significantly better. So I have negative 3.03 times 10 to the negative 19 equals negative RH. Remember, RH itself is positive, but we're doing negative 2.18 times 10 to the negative 18, correct? That's RH. It was right here. A slide from last try. It's convenient this chair was left in. All right. So that is a constant. You're not going to do this very often, but it is a constant you might see. All right. And then we had this equation, 1 over n final squared. I told you in the lab, or in the write-up, that the n final was what value? Okay, close. The real answer is 2, but we were squaring it, right? So this little piece here becomes 1/4 minus 1 over x squared. All right, are we okay with this so far? Okay, now, the biggest mistake kids will make from here is just algebra. You're going to divide both sides by negative 2.18 times 10 to the negative 18. When you type this in a calculator, you need to put this entire denominator in parentheses. If you don't, you do all the math on the exponent of 19. And that's not what we want. We want the math done to 3.03. All right. Then, do you have that? It's this one. That's awesome, but I need it to work. It's okay, though. Does anyone have this math answer right here written down? Point what? It's positive. You have two negatives here. Equals, now I'm going to simplify this as 0.25 minus 1 over x squared. You okay with that? Can someone back this number up? I see some doubting faces. All right, thank you. Okay. Subtract 0.25 from both sides, right? All right, and I get, did you do it yet? What's that? Well, this is a very good sign if you know math and you know this answer is supposed to be a perfect square. All right, now, algebra says that to get a variable out of a denominator, I multiply both sides by that, and that disappears, correct? And now I have this over x, or this times x squared. Are you with me on algebra? And then, to really get x alone, I have to divide both sides by negative 0.111. So I have negative 1 divided by negative 0.111 equals x squared. Now, 0.111 is 1/9, right? So this ends up to be 9-ish. Are we okay with that? So now I just have to take the square root of both sides. That's an ugly square root sign, but whatever. So this, we would say, x is equal to 3. Will you have a 30-second discussion about what this really means? It's not just a random number this time. X is equal to 3. Will you have a discussion? Go. Actually really close, but not quite correct. Anyone else? Knowing that that answer's close. Caitlin. It's energy it dropped. That's super close as well. If you combine both of those, you're really close. Bennett. Oh man, I hate when I crush hopes. You're close as well. It's not how many orbits. So let's look. No. You're all super close. Nope. All right, who said that? It's the initial. So what we're saying now, this circle, by the way, that represents the nucleus, okay? So we're not counting that. This is the first level, this is the second, this is the third. So, listen. Was really n initial equaling 3, wasn't it? So really what we just found is the electron went from the level to where? To the second level, because we said n final was equal to 2. That was part of the givens. You okay with that so far? Okay. Well, in the math it is squared, but n final, no, not in real life. It's still n. It's what level it's in, but math-wise we're going to square that function. All right. So when we found x was 3, it was the orbit that it was on, and then it fell 1 down to 2 and gave off red light, or light with 656 nanometers of wavelength. No, because that was this one. Let's take 3 minutes, and let's have you do the math for 486 if you haven't done it yet. and go. So here we go. How many were able to do this math and they got the answer of 4? Raise your hand. Okay, good. So tell your lab partner what 4 meant this time. All right. 4 was the initial level that the electron had to be on before it fell to the second. I need you to notice something because we have to have an aha moment here in about 10 seconds. You hopefully would notice when you got the answer 3, the energy was 3.03 times 10 to the negative 19th, right? You with me? That was the energy that you used in your math. When you got 4, what was your energy? All right, 4.09-ish times 10 to the negative 19. Do you notice this is a bigger number? Yes, which it should be. The larger the fall, the more the energy, and the shorter the wavelength. Are we okay with that? Short wavelength means high energy. If you want to test that yourself, draw on a piece of paper and make a really long wavelength. That wasn't very hard to draw. Like literally my hand moved up and down 3 or 4 times, right? But if I have a short wavelength and I'm going to cover the same distance, well, which one took more energy to draw? I mean, anyone can do that one. The bottom one did, right? The long wavelength would be representing the red light that we observed when an electron fell just one single level. Coming back to this now, we didn't do the math on the blue, but the short wavelength would represent the blue, and the blue ended up being when it fell from the 6th, right? If you did the math already, from the 6th to the 2nd. Larger fall, greater energy, shorter wavelength. Are we okay with that? The aha moment I need for you to have is how energy relates to wavelength and how energy relates to the electron falling from one level to another. Are we okay with that? Okay. We're not going to do more math on that. We're going to move on. Try and do those other 2. If you've already done it, just make sure your name's on it and leave it with me when you leave today. I did get an email that Heather was correct. We do have B time schedule all week except for Friday. There's an assembly. We don't have a schedule for that. I don't know what the assembly is, but I'm sure it will be amazing. Okay. The rest of the hour, we're going to work on quantum numbers and maybe electron configurations. Please notice, as I walked around, I saw someone put in their notes, test 1. Nice job. My plan is to test you on Chapter 7 only has 2 or 3 concepts, and they can be taught very thoroughly in a short amount of time. All right. So, our main objective today will be to understand quantum numbers. Quantum numbers come from the idea, by the way, name of this model of the atom right here. All right, that's Bohr's model of the atom. But it's super wrong, even though the math is super right, which is sort of weird. But when Heisenberg comes along and comes up with the uncertainty principle and the implications of that, it turns out Bohr's model cannot be right. So we come up with the quantum or wave mechanical model of the atom, and that's the rest of this chapter. The wave mechanical is based on math. It's not math you have to do or even think about, but it's pretty crazy and pretty cool. All right. So I had this slide up just for a second. These are the constants that I had programmed into my calculator a long time ago. They are not required. I also had Avogadro's number. We've done this a few times, so I'm not going to leave it up here. I had C in nanometers, I had H, and then I programmed HC, and that it doesn't matter if you don't want to program those because you already have these two in there, but it was just pushing one button. HC is just these two when they're multiplied because we do that a lot. E equals HC over lambda. All right, and then RH, you will not be tested on RH, but it is, I don't know, I'd put it in there if I owned my calculator. And Avogadro's number. These are the constants that I would have in my calculator. I'll leave that up for about 10 more seconds. If you want more than that, just take a picture of that. Or go to Canvas and watch this video online and look for the, I can't see the counter. Oh, I'm not. Am I recording? I definitely am. Where'd the thing go? I don't think I am. That's not good. All right, well, it says it's working, even though it's missing. Okay, moving on. All right, so a lot of this stuff will be confusing, but straight up awesome, in my opinion. So a guy named Louis de Broglie, he comes along and he says, hey, we have a wave-like behavior of light. I'm pretty sure there's probably a wave-like behavior of the electron. Okay? So he posited that if light can have material properties, matter should exhibit wave properties. So I just said everything. What I said wasn't a lie, but that wasn't this slide. He demonstrated the relationship between mass and wavelength, and it was that. Now, that's sort of weird if you think about it. That implies that since I have mass, I have a wavelength. And I do. We won't do the math because it's ridiculously pointless, but my wavelength is equal to h divided by my mass times my velocity. H is times 10 to the negative 34, right? My mass, that's not, I mean, it's a bigger number than most of you in here, but it's not significantly, that's not that big of a value. My velocity, so we're taking a really small number, we're dividing it by some meaningless numbers, so essentially my wavelength is a really, really small number. So we don't care about it, but if I have extremely small mass, now I'm taking a small number, but I'm dividing it by a really, really, really small number also, and I can get property, or I can get values that are actually reasonable. Like if I put the mass of an electron here, this is times 10 to the negative 28. That was 34. It's moving pretty fast. Now we have a wavelength that is scientifically valid and important. So we don't really worry about things with a large amount of mass. Things with small amount of mass we do care about. All right, Heisenberg comes along and he showed that the more precisely the momentum of a particle is known, the less precisely its position is known. All right, in many cases, our uncertainty of the whereabouts of an electron is greater than the size of the atom itself. So in a nutshell, he's saying, hey, if you know exactly how fast this thing is going, then you can't know where it is. Or if you know where it is, you can't really know how fast it's going. Because to know one or the other has to not exist. So for instance, when you get a speeding ticket, the requirement to get a speeding ticket is at a minimum, you must be moving, right? So where were you when you got your speeding ticket? Well, you were somewhere on 6th East. The policeman could never say your exact location of where you were speeding because to be able to speed, you have to not be where you were. Does that make any sense? All right. Now, it's easy for a car because it's huge. We can see it. We can touch it. But once again, when we get super small things, really, if we look and see an electron, the only thing we can say is that the electron is not where I just saw it. It's like a star. How far away are stars? A long way away. Light years away. So when I see a star at night, the only thing I know about the location of that star is that it's not where I see it anymore. It moved, right? It took light forever to get here. The only thing we know is it's not where we're looking. When we try and find the electron, we can't find it, but we can say it's probably right there. We don't know. It's probably right there. Sort of like when your parents, they don't know exactly where you are right now, but they know you're probably in my classroom. Do they know where you're sitting? Probably not, unless you're like super detailed. And how was school today? It was awesome. I sat in the second row back in my first hour class, 3 people from the wall. That's you. Whoa. But no one's going to do that when they get home, right? Your parents think you're in first hour, that you're probably in this class, and the likelihood that they find you anywhere else decreases the farther you move from this class. You okay with that? We're going to say the same thing about an electron, because we now know we can't know where it is. So we're going to say we know it probably is close to the nucleus, and that if I move away from the nucleus, the probability of finding it decreases. The nucleus would be this room. Your parents would probably find you close to this room first hour, and the probability of finding you would decrease the farther you moved away from this room. Could you be at Beto's? Sure, Floriberto's, sorry, to be exact. Sure, you could be. You could be Sam, lives in Perry, right? Sam's not feeling well. What's up, Sam? All right, but most first hours he's going to be in this classroom. Most of the time the electron's found in the atom. All right, so these beautiful pictures are actually what the atom looks like in our opinion now. I did. Isn't it amazing? I'm going to invite you to draw this as well. Now, you might think that my 6-year-old daughter drew this, but no, this is really organized and really awesome. So Bohr's model said, oh man, how far back was that? That the electron lived on orbits and went around the nucleus like a planet would go around the sun. It's typically called the solar system model, because it kind of makes sense. Sun in the middle, electrons behave like planets. We all right with that? That's Bohr's model, but that's not correct. Due to this wave nature of matter and the wave nature of the electron and the uncertainty principle, they had to change, and we'll come back to this picture in a second. They had to change the model of the atom to fit these ideas. All right, so the slides are just a little out of order. So along comes a guy named Erwin Schrödinger, who is famous for what? His dead cat, or is it dead? Oh, it's both. All right. Erwin Schrödinger developed a mathematical treatment into which both the wave and particle nature of matter could be incorporated. This is known as quantum mechanics. This was a super hard math problem I had to do in college. You had to prove this to be true, and it was the hardest math I ever did. You don't have to even look at the math. All right, but just know when the wave function, which is the math that he created, is applied, it's going to give you probability statistics based on the input numbers. And it's in a 3-dimensional space. Go ahead. Yeah. All right. Like we will tomorrow, technically. We'll run out before we really get there. Okay. So what we have, once again, we're going to have a big math equation. And when we say like this circle, the circle, it's a sphere, sorry. Everything's 3-dimensional when I talk. That's the place on a 3-dimensional graph where one of those values is a correct answer to solve the wave equation. Okay? It's a little bit weird, but they're answers that make the wave equation work, and they are probability clouds of electron distribution. All right? I know that's a little weird, but that's kind of where we're headed. All right? Solving the wave equation gives a set of wave functions or orbitals and their corresponding energies. Now, what did we barely say Bohr had? They lived on what? Orbits. What are we going to say, the wave mechanical? Where do they live? Orbitals. They are different. I'm going to draw them to show you how different they are. Here's what an orbit looks like. Here's what an orbital looks like. The only difference is this is three-dimensional, and the electron is probably found in here, like inside. The probability of finding the electron is high inside this sphere, but it still could be found outside the sphere. The probability just decreases as you move farther away. Bohr is, he said, he's dead by now. He's probably not dead by now, but when this was discovered. But he was way old and out of date. He said the electron lived on an orbit and simply spun around like a planet would, and could be found at any point in time because it's just on that orbit, I should say. All right? So the difference now is this is the probability of finding the electron. It is high within this sphere, and it is low without the sphere. All right? Each orbital describes a spatial distribution of electron density. An orbital is described by a set of 3 quantum numbers. Now before, yeah, go ahead.
So you're saying that you've never actually found
Not necessarily. We've gotten an electron and we've found it and we've looked at it. But we haven't been able to freeze an electron inside an atom and say, that's where it is and that's where it lives. We can't do that. They're always moving, and to know its location, we would have to destroy its momentum. In order to do that, we have to be at absolute zero, and we haven't been able to do that yet. So, yeah, and for us to really study an electron, we typically ionize some atom and get the electron alone. And then we can study its properties. All right. So we're going to talk about these numbers, quantum numbers, in a second. But that beautiful picture I have, here's how the atom looks. I'm going to have the nucleus. Now this is just going to end up looking like a bunch of scribbles. I have the nucleus. You all right with that so far? Okay. And then when an electron is added to an atom, or there's one electron hanging around an atom, it's going to reside in an orbital that's the shape of a basketball or a sphere or whatever. You okay with that? Now, it's not on that circle, it's inside that circle. Probably. Okay? Chemistry's awesome because it could be over here. But 99.999%, it's in here somewhere. Okay. This first circle can only account for 2 electrons. All right? But if you look at the periodic table, we eventually have to account for 118 electrons. So if there's more than 2, the next 2 electrons reside in a sphere of probability just slightly bigger. You okay with that? Now, it can hold 2 electrons. Who's with me so far? Okay? Now, look. It's very unique and weird, but the first 2 are probably in here. The next 2, they're also, by the way, probably in there. But we add a second layer now because the probability of finding electrons here is much higher than it was before. Because 2 electrons do what to each other? They repel. So as we add electrons, they still probably are found by the nucleus, but they also push each other away. So these have to get bigger. Now, the second one only can account for 2. All right? And then if we have more than 4 total atoms, the math solves for a completely different and weird shape. And it's called a propeller. That's terrible, but whatever. All right, we end up with clouds that look like this. That one's huge. Oh, crap. Whatever. We're going to leave it. All right. Now, these clouds, they are 3 independent clouds, but they're always drawn together. There's an up-down of the propeller, a left-right of the propeller, and an in and out of the board of the propeller. Are you okay with that? Like it comes this way, out of the screen. But I can't. Like, imagine I have a balloon going out here and one back in the screen. Okay, so they're 3 independent clouds, but each one of these, there's kind of a cool rule, this number repeats, each one of these clouds can hold 2 electrons. Now, it's 2 electrons, but there's 3 clouds. So how many total can this hold? 6 electrons. Okay. 1 for each half, if you want to say it that way. All right. Now, this accounts for how many total electrons so far? 10. Who's with me so far? I know this is weird. Caitlin is the only one that raised her hand because she had this last year. And she's like, I kind of remember this. All right. Now, there's certainly more electrons than 10, correct? Yeah, it would. Or it did. In a very complicated way. And here's the cool thing. Bohr's math is still to this day 100% right. Bohr's model was just not drawn the right way. Bohr's model said an electron, it would like go up if it was excited, but then it would give off light when it fell back down, right? And he was right. The math is still true. Here's what we're going to say now. An electron that lives pretty close to the atom, if it's given energy, it will move away and occupy a different shaped cloud. But that is an excited electron. It will fall back most of the time to its original shape. And if it was in a low energy, went to a higher energy, and then fell back down, the energy comes out. So now light is released when the electron probability cloud changes shape or size. Okay, and I know you're like, this is some of the weirdest stuff you've ever taught. Well, welcome. How is this still quantized? That's a super good question. Because every single P cloud, or I haven't named them P, every single propeller cloud or circle cloud, they all have the exact same amount of energy. A definite amount of energy, or defined or quantized. Okay, if we get past 10, go ahead, Island. So close. Yes, but it goes to the lowest available energy level that it can. Okay, it doesn't. If it's just chilling here and it's flying along, it's going to try and get as close to that nucleus as possible. But if all these are already full, that's not an option. You got to go to the back seat. And really, my children and my minivan is a really good example. When we're running out to go to church, I lose my. I can't stand it. They all fight over the front seat. But how many people can fit in my front seat? 1, because I'm already the driver. But yes, 2's fine. And then 4 kids rip the door off to try and get in the front seat. And okay, 1 gets in, and it's not hell yet, because there is the second row, which is acceptable, right? But I have 4 kids. So now the front's full. Now the next 2, it's not a bench. They're captain seats. You with me? So there's only 2 in that second row. And once those are full, there's always 1 kid that will bawl. Or if it's the 15-year-old that's 6'1", he will complain, I'm huge. I can't get back there. I'm like, just get your freaking butt back there. We're going to be late. Get out here faster. Anyway, where does the kid go? They go as close to the front as possible, but if it's full, they have to keep going. And going. You okay with that? All right. Now look, once we get past this level, I'm going to go fast now. We get another circle. It's just bigger. And after we get there, we get more propellers. They're just bigger. And that first circle that I drew that was bigger, guess how many electrons it can hold? 2.
It comes in at the 1900 circle.
They never, listen to me right now. No individual cloud ever holds more than 2. Now, are we going to eventually have more than 1 or 3 clouds? You bet we are. But an individual cloud holds how many ever? 2. Never more. It can hold 1 or 0, but it can't have more than 2. All right. Go ahead. Okay. Sort of. We'll get there. Uh-huh. Because up here, you're like, dude, you never hit the number 8. And that's why Isaac said 8.
Like the green and then all of the clouds are also.
Sort of, yeah. Yeah. Okay, here's how we get 8. Let me finish this terrible drawing. You ready? Okay, after we have, I'm just going to summarize. We then, Caitlin, are you ready? Post. We then add a different shape, and it will sort of look similar. It's like a 4-leaf clover. But, now remember, these weird shapes, why? Because that's what math spits out of your calculator on a 3D graph. That's really why. Okay, now, look. The popcorn shape, or the 4-leaf clover shape, it can only hold how many? 2. But there's 5 of them that arrange themselves in 5 different dimensions. So hold on. Here we go. Look at me. Look at me. I know it's weird. Yeah, class change window. We start with a sphere. That's easy, right? And it's not like a basketball with lines. It's just a blob. Does it matter what direction I orient it? No, it's just a blob. And then we had a bigger blob. You with me? But then we had a P, which was the propeller, which could go up and down, left and right, and in and out. It had 3 what am I doing? It had 3 dimensions, right? I've always had that problem. Numbers out here and on here never match. It had 3 dimensions. And we repeat that. They just get bigger. But eventually we get into these D clouds, which have 5 dimensions. And we don't mean like a 5th dimension, but we mean like up, down, left and right, in and out, and then like in and out, left, right, up and down, or whatever, like a diagonal, and then another diagonal. Like it's not like your mind should explode right now. But they're pointing in 5 different dimensions or directions. Are we okay with that? Now listen. Listen. Each cloud can hold how many total? 2. How many dimensions were there? 5. So that one can hold how many? 10 electrons. All right. Now, this repeats itself. We end up, I want to hurry because this is good. We end up with a bigger circle, bigger propellers, bigger 4-leaf clovers. I think that was 5. And then, don't worry, this is the last one. Then we get F clouds. And F clouds are weird. They sort of look like 4-leaf clovers, but they have like a donut in the middle of them. And each one of those can hold how many total? 2. But guess what? They orient themselves in 7 different directions, which means how many electrons? 14. Now, what? No, that's one whole cloud that you would draw 7 different ways. Now, I need this last minute, so let me have it 100% because this is cool. Look at the periodic table. Gosh darn it, where's my pointer? All right, the periodic table. I'm failing right now. Oh, I have that. The periodic table is this model. The periodic table is this model. How many did I say the first circle could hold? 2. Look, the first row has how many? 2. How many did I say the second circle could hold? 2. They're right there. But then I said we switched shape, and how many could it hold? 6. What's 2 plus 6? 8. There's how you get a noble gas. Then I said it repeated. It was just bigger. There was 2, and then there was the loopy-loopies, right? The propellers. And how many? 6. But then I said there's a circle, and then we get to Shiztown, and it's times 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we get 14. That model and the periodic table are the same thing.